Hello, this is Stefan Reimann from Zurich, Switzerland for the ICCM 2021. Welcome to my talk about a holographic approach to modeling memory. This talk is intentionally quite dense since this medium allows you to stop and eventually go back in the presentation. Well, experiments in this field have revealed a number of typical findings which are stable across various experimental settings, including different cognitive tasks. The series position curve is among the most famous benchmark findings and provides a good starting point for modeling. To avoid misunderstandings, I do not aim to provide a full-blown complex model with a great number of parameters, just the opposite. I will develop an elementary and simple computational structure with very few parameters and will show that this simple algebra already allows to qualitatively reproduce basic experimental findings. Various models have been employed to describe experimental data, including so-called distributed memory models and holographic models of memory. These models use two storage operations: addition like bundling for collecting items and multiplication like binding for representing associative, which is item-to-item information. While binding is realized by different formal operations, models agree in that bundling is done by common vector addition. Vector addition is a very convenient operation. Its convenience comes from the fact that changing the order of components in a sum does not change the value of that sum. But this particularly means that by using vector addition, bundling causes the loss of serial information. To represent serial order anyway, the loss of serial information has to be repaired in that serial information has to be reinstalled. For that purpose, various mechanisms are used, leading to different types of models. Position markers are postulated to code serial position in absolute terms. Sequential chaining is used to code serial position in relative terms. Weighting functions are introduced, mimicking primacy and recency effects along serial position. But the loss of serial order information can be avoided if, instead of common vector addition, a bundling operation is used which is not associative. This might sound like just weird exotic mathematics, but it is not. While it is our daily experience that many operations do not commute, such as rotations in three-dimensional space, we seem to be less familiar with operations which are not associative, but they exist and not only in formal computations, but also in nature. The example I would like to mention briefly is from population genetics and concerns mating. Mating is a non-associative operation. The argument is shown in the figure. Assume you have three species A, B, and C, or think about individuals. A and B mate, while their offspring mates with C, producing the offspring L. On the other hand, B and C mate, their offspring mates with A, producing offspring R. According to the laws of population genetics, the two resulting offsprings L and R are different. So mating is not associative. Furthermore, both offsprings will exist in the population. If mating were associative, we would look much more alike. Non-associativity creates diversity. After this preamble, we are ready to start modeling basic cognitive processes in memory. Quantitative modeling means computing, and there are then two basic questions to be answered. What are the elements used for that computation, and what are the operations by which computation is done? I call the set of elements to compute with the state space, and its elements will be called states. I use two operations by which states are manipulated and transformed. What is the state space and how does it look like? Let the list of items be sequentially presented. When item A is perceived, it induces an activity pattern in the neural field it is projected to do. This pattern is presented by a binary vector, which I call the corresponding state little a. Activity patterns are spread over a huge area, hence the state space is assumed to have some high dimension. The mean activity in a pattern serves as a basic measure for its sparseness. Sparseness is known to be of an essential importance in this context, so that a model should be able to integrate this. Finally, on the state space there is a metric defined, and the choice is not unique. In fact, many matrices exist that make the state space a metric space. In the following, I will not refer to a particular one. From a distance, one can derive a measure of similarity, and similarity will turn out to be an important building stone for the following. Due to time constraints, I will skip the mathematical details here, but it is anyhow worth mentioning that this definition of similarity allows to directly relate similarity to recall probability or accuracy, which is later needed for defining the series position curve. I will now define the two operations multiplication and addition. Addition defined here is different from vector addition and can be motivated as follows. See the upper part of the figure. Assume the two neurons A and B converge on a third one, C. If A and B are both inactive, displayed by empty circles in the picture, C will be inactive. If both are active, displayed by solid circles, C will be active as well. If only one is active, it depends on the threshold whether C will be active or not. The higher that threshold P is, the smaller is the probability that C is active. Both operations are formally defined in the right tables. The properties of these operations are important since they shape the outcomes of our computation. Particularly, each state is its own inverse, which will turn out to be essential for unbinding states. Second, the commutativity of multiplication relates to the experimental finding that associative binding is symmetric. Third, and most importantly, addition is not associative. The following is a necessary consequence of the so-defined bundling operation. Because of its non-associativity, one has to distinguish between two modes of addition. One is left associative addition, the other one is right associative addition. The corresponding left sum is denoted by L and the right sum is denoted by R, and both are different. This is the same as in the example of mating outlined above. In the single population, mating creates two different offsprings, L and R, which coexist in the population. It will turn out later that the left state L codes for the recency gradient, while the R state R codes for the primacy gradient. Details will be explained in the following. How does this now apply to the concrete experimental setting in which a memory list is sequentially presented to a subject who has to memorize it in order to fulfill some task afterwards, recognition or some kind of recall? Memorizing starts from a pre-experimental state eta. In Murdoch and Lewandowski, this state is empty. In Franklin and Muirhead, this state comprises a sufficiently large lexicon, which is a holographic collection of words and associations between them. From that initial state on, memorizing proceeds by successively bundling the states from the memory list. In detail, initially, both memory states are the same. They are equal to eta. They are denoted by L0 and R0 respectively. Now, item A from the list is presented. Item A is perceived, resulting in the state little a, which is added to the state L0 by left addition and to R0 by right addition. This gives states LA and RA. Now, the next item B is presented, and the corresponding state B is added to LA by left addition and to RA by right addition. The resulting states are LB and RB. After the entire list has been presented, two states L and R have been constructed, which can be regarded as the two components of the memory state, which represents the memory list lambda. The two states L and R are in fact different. The figure shows the distance of a particular item from the memory states R and L. Along serial position, distances from R increase while distances from L decrease. Distances directly translate into similarities. Similarity increases when distance decreases. In many tasks, after memorizing a Q item is presented. This Q activates the memory state stronger the more similar it is to that state. Activation of the memory state by the Q can be regarded as the strength with which the corresponding list item has been memorized in the memory state. Early items are stronger engraved in R, while later items are stronger engraved in L. Therefore, R codes a primacy gradient, while L codes a recency gradient. After the list was memorized, the two states L and R coexist. A presented Q will therefore activate both of them. Hence, the overall activation of the memory state is a sum of activations or a linear combination of them. A large rho means that the primacy effect is big, a large L means that the recency effect is big. The concave-up and asymmetric shape of the serial position curve is obtained by respective weighting of activities. These figures now compare empirical data with the simulation based on the algebra proposed. On the left, you see typical serial position curves of forward and backward serial recall. In the middle are data from free recall, while on the right, you see the results of simulations of the algebra proposed for different relative weights of activity gradients. Let me briefly mention Q recall to demonstrate the related method. In the paired list, A is bound to X, B is bound to Y, and so forth. Assume that Y is presented as a Q. The task is to recall the list item which was bound to Y. Computation, the formalism proposed, is simple. First, write down the memory state. For the sake of simplicity, we only consider the R state and skip the corresponding brackets. The R state is the right associative sum of products corresponding to item-item pairs. Then multiply the state with the QY and remember that Y times Y equals 1. Consequently, multiplying by Y will uncover B, which is indeed the item bound to the Q in the memory list. The right figure shows the activation profiles for different Qs. Our example, which is the Q is Y, is shown with red dotted lines. The red activation profile has a clear maximum at B, so that the answer will be Y was bound to B. Let me briefly summarize. Like other holographic models of memory, the formalism gains from the assumption that computation takes place in high dimension. Unlike other models, the operation for bundling is not associative. The guiding question was how far one can go using this elementary algebra alone, which is without any further assumptions. The answer turns out to be quite far, as it concerns the qualitative agreement with basic experimental findings. There are some important consequences of the bundling operation. First, during the collection of information, serial information is preserved. Second, a single memory list gives rise to two different coexisting memory states, L and R, where third, L codes the recency gradient, where R codes the primacy gradient. The serial position curve follows from a linear combination of these gradients. Other basic experimental findings can also be produced by that algebra. This includes the repetition effect as well as the serial position curve in queued recall as shown. At this point, it must be noted that serial recall cannot be described within this algebra alone, but needs an additional assumption. That assumption might be response suppression or an other feedback mechanism. The work by Franklin Muirhead provides a very interesting direction of thought. However, the simplicity of our framework, together with its capability to capture basic experimental findings, might encourage modelers to build a more full-blown model on top of that algebra. I am looking forward for your remarks, comments, critiques, and discussion in general, and thank you very much for following this talk.